Today on How It's Made Dream Cars, the Caterham 7, a lightweight British car designed for road, track, and race. The parking lot in front of the Caterham Cars head office in Dartford, UK, showcases various 7 models. All have striking design and state-of-the-art engineering in common. From the high-performance Superlight R400 to the futuristic Aero 7 concept or the Superlight R300 championship race car. The model dates back to the original 1957 design of the Lotus 7 by Colin Chapman. Based on a philosophy of performance through simplicity, Chapman designed the first 7 as a lightweight car, and people could easily assemble them themselves. The basic features of the car remain similar and true to the original 1950s design. The slim frame wrapped in a thin aluminum body and the traditional freestanding headlights are some classic features of the 7. With its fully independent semi-race suspension and rear-wheel drive, the 7 can be customized for casual on-road driving or for on-track racing. The Caterham 7 self-assembly kit includes a pre-assembled space frame chassis, the engine, and a set of pre-fitted components. Over 500 parts go into the making of a 7. The Caterham Technology and Innovation Center in Hingham is where design and engineering for the modern models take place. Engineers work on virtual designs on 3D CAD systems. One engineer works on the live axle rear suspension, while another works on the space frame chassis and body design. The CAD systems register the features of each car before it goes into production. At the Westbury Welding Shop, workers assemble pre-cut, high-grade steel tubing to form the chassis space frame parts. A welder assembles a chassis part called the bow on a jig and welds the tubes together at very precise angles using an electric TIG welder. He performs a visual inspection to make sure that all welding seams are solid and strong. Most parts are designed with open triangular shapes, which prevents the chassis from twisting. A worker starts welding the frame parts together on a chassis assembly jig. The welding around the front suspension must be very accurate to give the car the best possible handling. Thanks to its open frame design, typical of low-volume build, the assembled chassis weighs a mere 150 pounds. 2 workers now get ready to assemble the dashboard hoop. They clamp the hoop tight on a welding jig, and one worker holds it firmly while the other one welds. He spot welds the hoop on both sides, ensuring it is strongly attached to the frame. The workers unclamp the hoop welding jig and move it out of the way before grinding the weld profiles flat with the dual-action sander. The assembled space frame chassis is made of machined tubing with holes for bolts and sockets for the front suspension arms. It goes through a multi-stage electrostatic painting process. A worker rubs soap on a corner of the aluminum sheet used for the bodywork. Sheets come pre-cut and pre-formed, but need to be hand-formed around the angles. Using a high-temperature propane cylinder blow lamp, he heats up the aluminum to soften the sheet and make it more malleable and ductile. Then he folds the corner around the top bar frame of the chassis. When the soap turns brown, the worker knows the aluminum is at the right temperature, and he starts hammering the sheet to fold it tightly around the frame. He flattens the sheet around the top bar frame and keeps on hammering until folding creases in the sheet begin to disappear. He makes a coarse finish over the corner with a long, fine file to level the aluminum sheet as much as possible. He then takes a dual-action sander and runs over the corner using the multi-action rotary sanding disc to eliminate all traces of the bending. He finally polishes the metal with a cork sanding block, smoothing out the bodywork all around the corner to reach a mirror shine finish. The bodywork is now fully and seamlessly wrapped around the frame. The bodywork is composed of 2 aluminum sheets, which a welder joins around the bow using an electric TIG plant. The welder applies a polishing lubricant called tallow, which prevents the aluminum dust from contaminating the abrasive used to grind down the welding seam. The welder uses a belt sander to start flattening out the weld. He removes most of the welding profile before he takes an orbital sander to completely grind off the welding seam. He polishes the welding with a rubbing finishing block and cleans away the residue. The assembled space frame chassis goes to the coordinate measuring machine. A spring-loaded pointer measures the chassis to analyze the accuracy of the build. A computer then compares the data to design information recorded in the CAD system. The 8-spoke rim is a key feature of modern Caterham 7 designs. The forged and CNC machined aluminum alloy makes the rims light, while the V-spoke shape provides the wheels with resistance and flexibility. A virtual engineering software ensures that the features of the rim meet the requirements of the car. The computer performs stress analysis, corner fatigue, and impact testing. Design control and quality planning also involve casting solidification simulation. A computer program simulates the mold filling and the aluminum alloy solidification and cooling process. This step maximizes forging quality and minimizes production costs by reducing defects and scrap. The rims are made using a stamped forging production technology, a common technique used in the automotive industry. A blacksmith pours melted aluminum into the heating press mold. The smith closes the lid of the mold to prevent the burning hot metal from leaking out from the heating press. Stamp forming involves the application of continuous compressive and tensile forces on a workpiece with the single, slow, and controlled stroke of a stamp tool. As the stamp tool moves back up, it lifts the forged rim out of the forming die. Forged rims are 3 to 4 times lighter than cast rims, which helps reduce the total weight of the car. They have a better impact resistance and are far more durable, and enhance fuel efficiency, brake system life, and general driving safety. The forged rims go through a thorough material analysis process. An X-ray camera performs a geometry check, as well as a chemical and metallurgical strength analysis to detect any production flaws. The pre-finished rim lacks assembly holes for the wheel nuts and still has various forming marks. The CNC turning and milling processes remove all of these traces. The shape of the CNC machined rim varies depending on the type of alloy used and the type of wheel model being made. All rims go through the same 3-stage painting process before they are ready to be mounted with tires. First, an electrostatic spray painter applies a coat of white primer. The painted rim then goes to a CNC turning machine. The blade removes the paint and primer coats on the top edge of the rim. The machine sprays water to reduce the heat generated by friction of the blade against the rim, which turns at a speed of 1,800 rotations per minute. Once the turning is complete, the blade moves away, revealing the original aluminum finish of the rim. The turned rim goes through an electrostatic lacquer coating applicator, which applies a fine transparent film over the paint. Electrostatic painting and lacquering techniques make a uniform protective coating that is abrasion resistant. The engines used for the Caterham 7 series are small and compact. This 2-liter L4 engine is equipped with an ultra-small 40 amperes alternator and a 6-speed sequential transmission gearbox. A Caterham engineer makes the adjustment between the cylinders and the pistons. Using a carefully machined piece of metal called a feeler gauge, he checks the clearance between the piston and the cylinder wall and writes the measurements down to the millimeter. This meticulous process is intended to get the best possible fit between the pistons and the cylinder bores. The engineer inserts piston rings inside the cylinder. The rings fit into the groove on the outer diameter of the pistons to seal the gap between the piston and the bore. They prevent oil and gas from leaking out of the combustion chamber, thereby maximizing the effect of the displacement. The engineer checks the fit between the piston head and the rings in each cylinder. He finally measures the ring gap, which must be wide enough to allow for expansion, but not too wide to prevent leakage. The engineer now gets ready to measure the volume of the cylinder valve ports. He covers one valve port with a round plexiglass. Then he takes a volumetric pipette filled with a red-colored control fluid and starts pouring it into the valve crown. As the liquid empties from the pipette, it progressively fills the valve crown cavity until there is no air left under the plexiglass. The port volume is key to an optimal airflow. A good match between all 4 ports will ensure that all cylinders deliver an even displacement. The engineer now starts assembling the cylinder head to the engine block. He installs a gasket on the engine block. He then places the cylinder on top of the engine block, carefully aligning the assembly bolt holes with the sockets in the block. He applies high-temperature grease on the threaded head of the bolts, which endure high pressure and temperature inside the cylinder head. He starts manually assembling the bolts following a crisscross tightening sequence. This allows him to balance the pressure and the tension of the cylinder head on the engine block. Once he's done, he gives the bolts a final torque with a wrench. He must give enough torque to keep the bolts from slacking with time, but not too much to avoid stripping the threads. That could make them harder to remove for maintenance or repair of the engine. The engineer attaches a sequential racing transmission gearbox to the engine. The transmission belt housing is fitted to the engine block and connects with dowels, designed to align the transmission gear with the engine's crankshaft. The engineer manually inserts the assembly bolts and uses a wrench to give them the proper torque to securely fasten the transmission gearbox to the engine block. Compact 4-cylinder Ford engines like this one power most cars of the 7 Series. They come with a 1.6 or 2-liter displacement capacity depending on the model. By comparison, the Suzuki engine is much smaller. With its 5-speed gearbox and 3-cylinder 660cc turbo, it delivers 80 horsepower to the Retro 7 160 model. Various dashboard configurations are available for different Caterham 7 models. From the modern tachometer with electronic race instrumentation display to the retro dashboard controls with dial gauges and toggle switches. At the Dartford production facility, mechanics manually assemble various models from the Caterham 7 series. One mechanic applies high-performance double-sided tape on the dashboard hoop. Automotive tape provides a strong, secure contact bond, which does not slack when exposed to normal road vibration. The build mechanic, nevertheless, adds some mastic to the base of the dashboard hoop to seal the dashboard panel in place. He places the panel on the hoop and gently presses it onto the adhesive. The mechanic aligns it with the base of the dashboard hoop and pushes down firmly to ensure adhesion across all points of the panel. He wraps the base of the dashboard with holding tape until the mastic solidifies and adds tape on top of the dashboard to hold it in place while the adhesive sets. Underneath the scuttle with the windshield wiper post, this dashboard is mounted with classic dial gauges, rocker switches, and buttons. A build mechanic now assembles the aluminum fuel tank. He inserts the fuel sender unit and the level sensor in the fuel tank and pushes the unit firmly into place. He screws a plastic ring on top of the fuel sender and closes it with a wrench. He inserts the fuel tank underneath the boot board in the back of the car and aligns the fuel filler with the pre-drilled slot in the bodywork. He takes the filler cap and places it on top of the fuel filler neck protector. He inserts assembly bolts to hold the filler cap in place and tightens them using a small torque wrench. The fuel tank capacity varies from 8 gallons to 11 gallons, depending on the model. With a lightweight chassis and running gear, the cars have a reasonable fuel economy. Two build mechanics now install the front bonnet latches. They apply masking tape to protect the aluminum bodywork from scratching during the installation of the catches underneath the lock. First, they place the catch in position, aligning it with the lock riveted on the bonnet. They push the catch firmly against the tape to mark the position of the hole. Then, one mechanic drills a hole through the tape and into the bodywork. After removing the tape, the mechanic aligns the catch once again to the bonnet lock and holds it in place while the other mechanic rivets it to the bodywork. They repeat the process on the other side of the bonnet and finish the installation with 2 springs near the front suspension. A build mechanic now assembles the front suspension arm known as the wishbone. The independent suspension allows the front wheels to move independently. It also gives a better control over the camber angle of the wheels and helps minimize the roll or sway of the car on the road or track. A worker now assembles the engine to the chassis of the car. This supercharged Ford Duratec 2-liter 310 horsepower engine weighs just under 275 pounds. With the transmission gear, it fits tightly into the chassis of the 7620R. Near the end of the assembly line, workers mount the last pieces of the car. One mechanic mounts the rear wings over the rear axle. The fiberglass wing is fitted with a carbon fiber protector. Workers finish fitting the interior of the cockpit of another car. The car is equipped with an engine coolant radiator at the front. One mechanic mounts a rear roll bar to the chassis behind the cockpit of the car. Another worker installs the side exhaust pipe and silencer before the car moves ahead on the assembly line. A mechanic mounts the wheels on this 7620R. The forged rims are fitted with track-inspired tires, designed to optimize both on-road and on-track performance. He gives the wheel a manual spin to ensure it turns freely on the axle. Once all 4 wheels are assembled, the mechanic installs the nose cone. There is plenty of venting space to allow the radiator to properly cool the engine. The front bonnet also has built-in cooling vents and air intakes for the engine. The mechanic finally secures the bonnet in place with the bonnet latches. The car is up on the vehicle ramp for final inspection. From underneath the chassis, we have a clear view of the front suspension, the engine and transmission tunnel, and the live axle at the rear of this 7160. A driver takes a car to the parking lot before going for a 12-mile road test. 2 road-ready cars wait to go out to the test track. The AeroScreen windshield is a standard feature of many 7 models. The 160 model is the modern 7, closest to the design of the original Lotus 7. This one features an aluminum dashboard and right-hand drive configuration. Caterham 7s are renowned for their handling characteristics and acceleration. The 7620R supercharged engine delivers 310 horsepower. It can accelerate from 0 to 60 miles per hour in less than 3 seconds and reach a maximum speed of 155 miles per hour.